Okay, let's do some R lab for the cross-validation we just talked about. So in this lab, we will do validation set method, leave one out cross-validation and k-fold cross-validation. Okay, k-fold. Um, mm, so we will use the auto data that we've talked about a couple times. So we first attach this library of the book, and also we have a function from this boot library which help us to do the cross-validation. So we have a function directly that we can use to do cross-validation. Okay, that's about the packages. And if you notice, I set a seed here, which setting a seed would would allow your code to be reproducible. What that means is that if you set the same seed, no matter who get the code and run with random sampling, random sampling, it will give you like the same sample with this seed set. So this would guarantee like if you run the code that like this R code file, that you will get exactly the same answer. So yeah, when you work with randomness, it's always a good idea to set the seed. So in order to guarantee reproducibility. Okay, we'll start with the random set method. Now we use a sample. So we randomly sample half of your data set, half of the data set as our training data set. So this will give you the indices. So we will, without replacement, so you can see this replace equal to false. Without replacement, we will sample 196 indices out of 392 indices. So basically we are sampling from the vector of from 1 to 392. We will sample half of its size without replacement. Okay, once we get the training indices, we can use this LM function and specify a subset being this train. So this is the indices for the training data set. So once you specify this, then the function would know we will use a subset of this data set to run this model. Okay. And if you want to do a prediction, okay, let me run this first. Okay, and yeah, and we will attach this data set. And in order to do a prediction, so this is to do a prediction for the whole data set. This whole data set auto. We'll get this. So if you pay attention, this fitted, it has this many. This is the length, 392. This is the whole data set. And if we want to get only the testing data, the predicted testing data, so we can do this fitted and remove the indices for remove the rows corresponding. Oh, well, this is a vector. Remove those elements corresponding to the train indices. So this way you get only the testing, predicted testing data. Okay, and if we want to check the squared error, mean squared error of this testing data set, we can do this MPG minus So MPG is the Y we are predicting, and this fitted is the predicted value with your model. So you take the difference of the predicted from the true value and take only the testing data set. So this whole vector would be of length 392, and we remove the element corresponding to the training data set. So this way we get the residuals or the error term corresponding to the testing data set. And then we take the square and then take the mean of them. We get our mean square error of the testing data set. Okay, so let's take a look. So this is your mean squared error with your with the testing data set. And well, I have another example where you can do sort of a model comparison. I mean, like manually, just by using this training and validation method to compare this model. So now let's do this polynomial regression for this prediction of MPG with this house power. And we will compare with quadratic regression and also cubic regression. So look at this one. I'm doing this linear model with this MPG regress on this polynomial term. So this would include both the linear term and the quadratic term in the model. And also we specify we will use a subset of this training data set to run this model. So let's run it. And similarly, we can get the mean squared error corresponding to this model. Okay, lm.fit2. So this is the mean square error if we do this polynomial regression of order 2. So quadratic regression, we will get a mean square error of 18.7 something, which is a bit lower comparing to the previously like linear model with 23.3 mean square error on the testing data set. Okay, so this would be a better model with this quadratic term. Oh yeah, I put this summary here just to show you it has both the quadratic term and the linear term here. Okay, this is for the linear term and this is for the quadratic term in the regression model. And similarly, let's do this cubic regression. Okay, we will run this lm.fit3, and this would have 3 terms: cubic, quadratic, and linear term. And we can calculate the mean square error corresponding to this cubic model. And we can tell it's 18.8, about 18.8. So this is a bit higher comparing to this quadratic model. So that means this quadratic model is the best out of the 3. Okay, so this is sort of you are comparing different model with a training and validation or training and testing data to tell which one have the better prediction power, which give you smaller error on the testing data set. So to illustrate, we're setting the to make sure it works with no problem. Let's change to a different data set. We'll just set another seed. So when we sample this, when we do this sampling without replacement, it will take a different sample. Okay, so this training data set would be different from the previous one. So let's just do it again with a different training and testing split. So it's still half and half split, like 50% of training, 50% of validation, but we're just use a different training data set and different testing data set because we have chosen different indices for training comparing to the previous set of code here. Okay, oops, yeah. If we run this whole thing again with a different seed, we can tell, well, you can notice those mean square error has changed, but the conclusion, excuse me, the conclusion would be the same with this quadratic regression being the best model because it gives us the lowest mean square error on testing data set. Okay, yeah, then it's the leave one out cross validation. So you can do this leave one out cross validation with this with GLM and this CV.glm. So this GLM is a generalized linear model. If you don't tell it otherwise, it does linear regression. So by default, it will give you linear regression. And also, it's what we used for a logistic regression when you specify the family, distribution family as binomial. Let's first make sure this GLM will give you the same answer with LM if you do not give other arguments for this GLM. Let's just make sure they give you the same coefficients, okay? This is just trying to tell if this coefficients equal to this coefficients. And it says true, so that means they're equal. And we will use this cv.glm from this library to run cross-validation for us. Okay, so this is how we do it. We will just provide the data set and the model that we originally used here, like this. This is the original model of this regression model, glm.fit. So you just supply the data and the glm fitting model, and this will give you, oops, this will give you, yeah, it takes a little bit. You can get the mean square error by calling this delta out of this object. Okay, so this delta will give you the mean square error. Well, these two are quite similar, right? Oh, by the way, the value without specified, without any other instruction to this cv.glm, it will do the leave one out cross validation. So this is the error for leave one out cross validation. Okay, so that is the mean of the mean square error for each repetition. So if we want to use this to compare different feet of the polynomial model, we can use a for loop, as I put here. So I first initiate a vector of length 5. So this is a vector of 5 zeros, okay? And I put them in a loop and do this GLM with different level of this polynomial regression. And I calculate their error correspondingly and extract the cross-validation error. So let's just do this. Yeah, because it's a loop, it takes a little bit, it takes longer, apparently. And if we take a look at the cross-validation error, so yeah, this is what we get. This would be for polynomial of level 1, so that's the linear model, will be the linear model, and this is the polynomial, the cross. So let me take it back. So this is the cross-validation error of the polynomial regression of level 1. So this will be the linear regression, okay? And this would be the cross-validation error for the quadratic regression, and then cubic, and fourth order and fifth order. Okay, and in this way we can compare like which would be the best model we should use for the polynomial model. So still this quadratic regression would be the best. So I should equal to 2 in order to get the lowest cross-validation error. Okay, and the last example is to do a k-fold cross-validation. Okay, and we can still use this cv.glm, but we just need to tell this function how many folds we want. Okay, so by default, this cv.glm is to do leave one out. So the argument k should equal to 1 for this function. So when you specify k, so this is the number of fold. Let's just make sure. So yeah, this is, if you do question mark in cv.glm, it will give you like k is the number of groups into which the data should be split. In the default, well, not k equal to 1, k equal to n, sorry. So by default, well, yeah, the default is to set k equal to the number of observations in the data. So that is k equal to n, okay? Now we set k equal to 10. We're going to divide the data into 10 groups, and we're going to do a 10-fold cross-validation. So similarly, we set a seed here to make sure this result is reproducible, and then we do a loop to compare I also use I up to 10. Okay, so let's compare. So yeah, this is the cross-validation error for tenfold cross-validation error. And if we make a plot of the error, I'll add some line to it, and you can tell, well, this I equal to 7 would give us the lowest cross-validation error. Okay, so if you look at this, well, number 7 would be this one. Okay, this is slightly lower than those. So that's theoretically is the best model, but it's, well, involving 7 terms. It's quite a complex model. Okay. Yeah, let's just stop here for the cross-validation lab.